All right, this is an update from the OHDSI Working Group for August 2022. I am Robert Miller, and let's get started. The goals of the working group, the broad long-term vision is to enable studies of place-related data in conjunction with the longitudinal patient-level data in the OHDSI ecosystem. Our short-term focus is to develop functionality to automate retrieval and transformation of publicly available place-related data into a standard representation. Our last few updates have been quite vague, so I'm going to get a little bit into the nuts and bolts here of what we're doing. We're doing a development sprint on the backbone of the PostGIS design and the related R functions. A vertical sprint to move from conceptual to code. We've been doing a lot of discussing and sort of planning stuff out, but just putting things in place so we have something actually to look at and talk about and finalize everything. Proof of concept, discovery of gaps, finalizing the model. We're starting with the known use cases and expanding out with an emphasis on incorporating a variety and representation of data sources. Breadth over depth, and expanding automation and functionality to be capable of handling all types of data sources. So that's direct downloads, APIs, different file formats, zips, CSVs, whatever. And then the parameterization of API calls and how those vary, and off messages and everything needed to get anything from anywhere, which is understandably a lofty goal. The approach is with an emphasis on extensibility and automation, and those are the key that we're trying to do here. You can bring in a geospatial data set and do that manually, and it'll take forever. But to do that in a very, very light way for the end user. So we're building a repository of functionality. It's not a data repository of any data in a standard format. Rather, it's a repository of the specifications you need to automate populating that data locally in your PostGIS instance. The development stack is PostGIS, which I've mentioned. It stores the place-related data and metadata. It has a built-in local geocoder, which is why we were starting with that. It has the standard place-related data representation, that's where it's stored, as well as the metadata or specifications needed to automate the ingestion. The other portion is the R, just utility at this point, which is used to populate that data in PostGIS, translate the specifications into reformatting the data. And eventually, the translation between OMOP and this instance, which is actually fairly straightforward. Building, translating, combining, displaying the different layers, and then putting it all in a UI, likely Shiny, but then to be built in with other apps like Atlas as well. So the two core concepts here of what we're doing and why it has potential and why it's taking us so long to do this is the first I mentioned is the standard representation for any place-related data. This is stolen from OMOP, the same sort of principles where OMOP is person-centric, the representation is geometry-centric. So any data source is represented in the same format, two tables. The first is geometry, whatever that may be. It's pretty flexible, points, lines, polygons, and then attributes about those geometries. It's in that attribute structure is almost identical to the measurement table, but just obviously with different linkages to it. The data is formatted in the same way, but in separate tables. So that allows tooling to leverage a small set of functions that apply to all of the data. And metadata and indexing tables allow tooling to run against data in disparate databases or schemas or tables, yet query it as if it was one large data set. And the other core concept is automation to focus on that. And that's of retrieving the data from its source, translating it into the standard format, and populating it. The metadata and mapping specifications needed by the tooling are where and how to download the data from its source into a staging, basically in R. For geometry object specifications for how to translate that into a geometry standard, and for features, which are more or less like concepts, specification for mapping into the attribute standard. So standard representation is fairly straightforward. It's a geometry table and an attribute table. And again, on the right, you'll see that it looks very similar to the measurement table. And that has a foreign key to the respective geometry table. The geometry is basically holding the polygons and the source values of how you're coding to that, basically the identifier in which you're looking to, a FIPS code, GeoID, whatever that may be. And the backbone is what we've been focused on. Shout out to the OHNLP working group. This is a schema. It has 4 tables in it. Basically, the data source holds most of the information to populate everything except for the features themselves. and the feature index is going to hold the definitions for the actual attributes that you're bringing in. The index tables are more or less routing tables to get to the data. It's saying this data source you can find in this schema, in this table name. Tilling uses the schema table mappings to parameterize queries as if it were two large tables without the efficiency loss of that actually being the case. You can see a example here of what a row in the attribute index would be. It's basically just an identity column, which geom it's referring to, where you can find it in the data source that we mentioned before. These mapping specifications, which were initially daunting, are seeming almost like that. So we're doing it in JSON right now. It's interpreted by R to translate from the source to the standard. Each object of that JSON is a column of the destination table. Ideally, these are programmatically generated. You create one for a data source, and if they're common in the same format, you could just generate the rest of those, hundreds at a time. 3 mapping types, select, so you're just grabbing a column verbatim. Hard code, you're assigning a static value, and code, when things get more complex, when you need to choose from multiple columns or use some sort of conversion of some sort. Basically, it's just a snippet of our code as a string. There's an example at the bottom of pulling in the county data from census and translating that into the columns you can see on the right that would then be used to populate the geometry table. So the mapping specifications themselves, they persist also with these features. Typically place-related data is in a wide format, or it does vary a lot, but where each column is a separate observation or measurement. And we're translating more in EAV structure, similar to OMA, where you can have a geometry and each row is a observation measurement about that geometry. Those specifications right now are in the feature index. I think we're going to change the name of that table because it might be confusing to those in the JS realm. And you can see an example table here of the social vulnerability index by county. Right now, it's pretty simple. There's going to be added metadata and ideally links to ontologies for these so that we can navigate these easier. But basically, the mechanism to import it into the standard format is part of the definition here. You can see on the far right. And the idea would be with a library of features and respective dependencies, you can pick and choose a single feature from a data source and pass it into a function, say like load feature with just that ID. And it would go and get the data. It would populate the rows in the index tables if they're not already there, populate dependent geometry table if it's not already there, and then translate that data into the standard representation and import it. So very, very hands-off, very easy for the end user is the goal. So the next steps of what we're doing, what we need is additional dedicated developer effort. That's something we've struggled with for a while. So if you are interested in this and think it's a cool idea, we could certainly use your help. More use cases, more data sets to incorporate to test this functionality is as widely applicable as we think it is, especially any international data sources. We've been working a lot with US data, so anything outside of that. When we're further along, community effort to build specifications to integrate new sources. This is meant to be basically a jumping point to which the community can add different specifications and add to this building repository and have it be this potentially very large resource for people to leverage. Where we're heading, we're releasing this development version of the implementation, creating a repository, the ability to search and append new sources. Integrating with the OHDSI stack in various ways, and then a tool, just a simple one, to generate these mapping specifications I was referring to more easily integrate new sources. And that is it. That's our update. That's what we're up to. We'd love to have more contributions. If you have questions, please reach out.